January 1953. A storm surge rolls down from the North Sea with no warning and no mercy. The seawall breaks, the water comes in the dark. Over 300 people in England drown in their beds, in their streets, in their homes. In the Netherlands, more than 1,800 more never wake up. And in London, the water rises to within a breath of catastrophe, stopped not by engineering, but by luck. That luck would not last forever. Welcome back to the channel. Today, we are talking about one of the most audacious flood defense systems ever conceived by human engineering. A project that took years of political debate before a single shovel touched the ground. A project that required engineers to invent solutions that had never existed before. A project that sits in the Thames right now, mostly invisible to the millions of people who live under its protection every single day. This is the story of the Thames Barrier, a steel wall built across a living tidal working river to hold back the North Sea itself. This is not just a dam. It is not just a gate. It is a machine. 10 moving pieces of steel, each one engineered to lie flat on the riverbed and then rise, silently and with enormous force, to seal off the most important river in the English-speaking world. It is a machine that protects approximately 125 square kilometers of central London. A machine that stands guard over more than 1 million people. A machine that has been called upon to close more than 200 times since it first became operational. And every single time, it has worked. But to understand what the Thames Barrier truly is, you have to understand what it was built to stop. You have to go back to that January night in 1953 and feel what it meant when the sea came ashore and there was nothing to hold it back. The North Sea is not a gentle body of water. It is shallow, narrow, and funneled, shaped by the geography of Northern Europe in a way that amplifies storm surges rather than dissipating them. When a deep area of low pressure moves across the Atlantic and drives a wall of water south through the gap between Britain and Norway, that water has nowhere to spread. It compresses, it accelerates, it piles up, and the Thames estuary opens like a wide mouth pointing directly at London, pointing directly inland toward one of the most densely populated cities on Earth. In 1953, the city was not ready. The Victorian embankments and aging sea defenses could not absorb what the North Sea sent that January night. The water overtopped them. It poured into basements and ground floors and living rooms across East London, across Essex and Kent, across the flat coastal lands of eastern England. And when the water retreated, the dead were counted, and the politicians and engineers looked at each other and asked the question that would define the next 3 decades of civil engineering in Britain. How do you protect a city like London from the sea? Before we continue, if you are new to the channel, hit subscribe now. We go deep on mecha projects, engineering challenges, and the human stories behind the structures that quietly hold our world together. Stay with us until the end of this video, because the hidden life of the Thames Barrier, what happens beneath the water, what happens inside those gleaming steel piers. What most Londoners never see is the most extraordinary part of this story. At first, there was only the river, wide, tidal, brown, and alive, no barrier, no gates, no piers rising from the water, just the Thames rolling east through Woolwich Reach, carrying barges and ferries and the commercial traffic of a working port city. The river had been there for thousands of years, and for thousands of years the city had lived alongside it, and feared it, and sometimes been destroyed by it. The idea of putting a structure across it, a permanent closable structure, across a navigable tidal river, without blocking shipping, without wrecking the ecology, without simply shifting the flood risk to somewhere else, was by any reasonable measure almost impossible. The engineers knew this. They debated it for years. The 1953 flood had made action politically urgent, but urgency and solutions are not the same thing. A government report recommended a flood barrier as early as 1953. Committees were formed, studies were commissioned, and then more committees. More studies. The problem did not go away. In 1965, a report by Herman Bondi, one of Britain's most eminent scientists, concluded that the risk to London was real and growing, and that the time to act was now still. The debate continued. If you simply build a solid wall across the Thames, you kill the river as a port. The whole point of the Thames is that ships can sail up it. Close it off permanently, and you destroy the commercial heartbeat of the city. If you build a system of floodgates that drop down from above, you need enormous overhead structures, towers, cables, cranes, rising high enough to allow tall vessels through when open. That means extraordinary engineering in both directions. Massive height when open, massive strength when closed. If you try to divert the floodwaters through tunnels or alternative channels, you are moving the problem rather than solving it. The volume of a North Sea surge is simply too large to redirect. Nature does not cooperate with tunnels. Each one either blocked the river, could withstand the surge pressures, or simply couldn't be built in a tidal river environment without creating engineering problems larger than the one it was trying to solve. So the solution was not conventional. It was not a wall that drops. It was not a gate that rises from above. It was something that had never been built at this scale before. The solution was a gate that rotates. A gate that, in its resting position, lies flat on the bed of the river, invisible out of the way, offering no resistance to the water or the ships passing above it. And when the signal comes, when the tide data and the storm surge predictions tell the operators that London is in danger, that gate rotates like a visor closing, like a shield swinging up from the ground, until it stands vertical in the water, forming a solid barrier against the incoming surge. 10 gates, spanning approximately 520 meters of river, 4 main gates, each 61 meters wide. Wider than the opening of the Savoy Hotel is long. 6 smaller gates flanking them, covering the shallower water near the banks. And each of those 4 main gates, weighing approximately 3,700 tons, not lifted by cranes, not hauled up by cables, rotated smoothly, hydraulically, precisely by machinery housed inside the concrete and steel piers that stand between them. This was not simple. This was one of the most complex pieces of mechanical and civil engineering Britain had ever attempted. Construction began in 1974, and from the first day, the engineers faced a challenge that would define everything that followed. You cannot simply build in the Thames. The Thames does not stop for construction. It rises and falls twice every day with the tide. It carries silt and sediment and current. It is a living system, a working river, used by commercial traffic and pleasure boats and ferries, in the middle of one of the world's busiest cities. Every piece of this project had to be built around the river's schedule, not the other way around. The first task was the riverbed itself. Before anything could be built, the engineers needed to understand exactly what they were building on. Survey teams went into the water. They mapped the Thames bed at Woolwich Reach in extraordinary detail: the depth, the sediment layers, the rock formations beneath, the underwater current patterns, the silt behavior under different tidal conditions. They drilled core samples. They analyzed the geology. They needed to know not just what was there, but what it would do under the weight of the structures they were about to place on it. What they found was not simple. The riverbed at Woolwich was a complex mixture of materials: gravel, sand, clay, and deeper chalk formations. The load-bearing capacity varied across the width of the river. This mattered enormously because the piers, the massive concrete structures that would house the gate machinery, needed foundations capable of carrying thousands of tons in a tidal river for generations. Get the foundations wrong, and everything built above them was at risk. The solution was caissons. Enormous precast concrete cylinders manufactured on land, floated out into position on the river, and then sunk carefully, precisely, under controlled conditions through the riverbed material until they found solid bearing. Each caisson was a feat of engineering in its own right, designed to withstand the water pressure during sinking, to resist the current, to be positioned accurately in a tidal river where conditions change every 6 hours, and then to be sealed and filled with concrete to form the permanent foundation for everything above. Imagine standing on the deck of a construction barge in the middle of the Thames in winter. The tide is running, the river is cold and dark, and you are trying to lower a concrete cylinder, weighing hundreds of tons, into an exact position on the riverbed, a position marked on a survey plan, a position that must be accurate to within centimeters using cranes and cables, and the collective experience of workers who had never done anything quite like this before. Every meter of descent mattered. Every degree of tilt had to be corrected. Every change in the current had to be anticipated and compensated for. The water did not stop. The tide did not wait. This was not easy. This was an act of extraordinary precision performed in one of the most unforgiving environments a civil engineer can face. Once the caissons were in place and the foundations secured, the construction of the piers began. The piers are not just structural supports. They are not decorative elements. They are operating buildings, each one a fully functioning machine room, housing the hydraulic systems, the control equipment, the power supply, and the mechanical arms that rotate the gates. Each pier had to be built to industrial strength, sealed against the river, accessible for maintenance, and capable of operating in conditions ranging from summer calm to North Sea storm. They are simultaneously a foundation, a machine room, and an architectural statement. The distinctive roof of each pier, that curved stainless steel clamshell shape that has become one of the most recognizable silhouettes on the Thames, was not a decorative afterthought. It was engineered to house and protect the massive rocker arm mechanisms inside, to shed water, to withstand wind loading, and to allow maintenance access. The steel cladding was chosen for its resistance to the tidal, saline, industrial environment of the river. Every curve, every joint, every panel was specified to survive decades of exposure. Then came the gates themselves. Building a gate 61 meters wide and weighing approximately 3,700 tons is not a task you do in the middle of a river. The gates were fabricated on land in workshops designed specifically for this project, using high-strength steel plate, curved and formed and welded into the precise hollow shell geometry that gives each gate its extraordinary strength. The hollow interior is not wasted space, it is structural. The curved shell acts like a stressed skin, distributing loads across the entire surface rather than concentrating them at individual points. It is the same principle that makes an eggshell stronger than it looks. Each gate section was fabricated, inspected, tested, and transported to the river in stages. The assembly process required coordination across multiple fabrication sites, transport logistics that had to account for the size and weight of the components, and final on-site assembly work that had to be done. Again, around the tidal schedule of a working river, the installation of the gates was among the most technically demanding phases of the entire project. Each gate had to be lifted carefully, slowly, with enormous cranes, and positioned at the ends of its pier supports. The trunnion bearings, the massive pivot mechanisms that allow each gate to rotate, had to be aligned with extraordinary accuracy. And the gate had to sit perfectly in its sill, the concrete sill on the riverbed that it seals against when closed. A gap of even a few centimeters in that seal would allow water to pass through. The seal had to be near perfect. The alignment had to be held not just on the day of installation, but for decades of tidal movement, thermal expansion, and contraction. The hydraulic operating systems were installed inside the piers simultaneously with the gate fitting. Each gate is rotated by a pair of hydraulic arms, enormous cylinders, driven by high-pressure hydraulic fluid, capable of generating the force needed to move thousands of tons of steel against the pressure of a tidal surge. The hydraulic systems were designed with multiple redundancies, backup power, secondary control systems, emergency operating modes, because a flood barrier that fails to close when London needs it is not a flood barrier. It is a catastrophe. The control systems connecting all 10 gates across 520 meters of river had to work as a single coordinated machine. When the Environment Agency operations team at the barrier's control room receives data showing a dangerous surge approaching from tide gauges, from meteorological stations, from the North Sea flood warning network, they have a limited window in which to close the barrier. The gates must be rotated in the correct sequence, coordinating the movement of 10 separate pieces of steel, each controlled by its own hydraulic system. And they must close completely, and they must seal. Before the surge arrives, getting the operating systems right required extensive testing, not just of individual components, but of the complete integrated system. Every hydraulic circuit was tested, every seal was inspected, every control connection was verified. The engineers ran the gates through hundreds of trial closures before the barrier ever faced a real flood event. They tested in calm conditions and in running tides. They tested with simulated power failures. They tested the backup systems. They tested the emergency overrides. Then came the riverbed works beneath the gates. The concrete sills, the structures that the gates seal against when closed, had to be placed on the riverbed with the same precision as everything above. Divers worked in the dark, turbid water of the Thames to inspect and prepare the sill positions. Underwater concrete work was carried out using techniques adapted for the specific conditions of the Thames, the limited visibility, the cold, the current, the tidal cycle that gave workers only a narrow window of slack water in which to operate safely. Every pore had to cure correctly. Every surface had to be flat and clean and true, because when that gate comes down and seats against the seal depends on the quality of that surface. Throughout the entire construction period, approximately 8 years, from 1974 to 1982, the Thames remained open. Ships passed through the construction works. Ferries ran on their schedules. The river continued to do what it had always done, while around and beneath it, one of the most complex civil engineering projects in British history took shape. This was not a coincidence of timing. It was a deliberate engineering requirement that shaped every decision about settuning, temporary works, access. The river came first. The construction worked around it. The barrier became operational in 1982. It was formally opened by Queen Elizabeth II on the 8th of May 1984, and at that moment, London had something it had never had before in its entire history, a system capable of closing the Thames against a North Sea flood surge. Most people who see the Thames Barrier from the riverbank see 10 gleaming steel roofs rising from the water. They see the wide gaps between the piers where ships pass through. They see something that looks like sculpture, unusual, beautiful, unmistakably purposeful, but they do not see the gates. They do not see 4 curved shells of steel, each one the width of a city street, lying flat on the riverbed beneath the water, invisible, patient, resting in their open position, waiting. They do not see the concrete sills poured into the riverbed, machined to tolerances measured in millimeters, that those gates will one day seat against. They do not see the hydraulic cylinders inside the piers, the enormous actuators, each one capable of generating forces measured in hundreds of tons, kept pressurized and ready to move. They do not see the trunnion bearings, each one a precision-engineered pivot point carrying thousands of tons of gate weight through decades of tidal movement and thermal cycling and vibration. They do not see the maintenance teams who work through every week of every year, inspecting seals, testing hydraulics, clearing debris from the sills, checking gate alignment, running test closures, because a barrier that has not been maintained is a barrier that will fail when it matters most. They do not see the operations room where, on more than 200 occasions since 1982, engineers have watched the tide data come in, watched the surge predictions track higher and higher, and made the call to close the gates, knowing that somewhere upstream, in Twickenham and Battersea and Westminster and Southwark, 1 million people are sleeping without knowing how close the water came. Every tide matters. Every seal matters. Every hydraulic test matters. Every maintenance inspection matters. Every one of those more than 200 closures has been a real event. Real water, real pressure, real lives in the balance on the other side of a steel gate lying on the bottom of the Thames. The 1953 flood killed over 300 people in England. That night the sea came, and there was nothing to hold it back. The response took years of political will and engineering ingenuity to produce years of debate, years of study, years of construction, years of testing. It was not fast. It was not cheap. The final cost reached approximately £534 million. It required engineering solutions that had never been used at this scale before. It required workers to build underwater, in a tidal river, in the middle of a city, without stopping the river from doing its job. But it worked. The Thames Barrier is not the largest structure on the Thames. It is not the tallest. It is not the oldest. But it is, in every meaningful sense, the most important, because every other structure on that river, every bridge, every building, every embankment, every hospital and power station and underground line depends on it. Without the barrier, The next big surge is a question of when, not whether. With it, London has bought itself time. Time to think, time to adapt, time to plan for what comes next, because the barrier was designed for the conditions of the 20th century. The sea is rising. The storms are intensifying. The window in which the barrier can do its job is narrowing, somewhere in the future. Not today, not tomorrow, but somewhere London will need to decide what comes after this. A new barrier, a higher barrier, a different kind of defense altogether. But that is a question for the future. Today, the gates lie flat on the bottom of the Thames at Woolwich Reach. The hydraulic systems are pressurized. The control room is staffed. The tide gauges are reading. And if the North Sea decides tonight is the night, if the pressure drops and the wind backs and the surge builds in, the shallow funnel of water between Britain and Europe, the signal will come and the arms will move, and London will sleep. If you found this story as extraordinary as we did, please subscribe to the channel and leave a comment below. Do you think the Thames Barrier will be enough, or does London need to start planning something bigger, something bolder, something for the century ahead? We would love to hear what you think. Thank you for watching.